Good evening, my loyal viewers. It has been a very long time. This is the Heavy Metal Chemist, and I will apologise for my absence. I've been starting a new job and doing various other things with life. I'm going to do a quick lecture on a subject which is quite dear to my heart and I want to find the thing to work, and that is fire. Now, for those of you that know me in person, you will know that I did my doctorate in fire, but pull that out before I burn my finger. Basically spent 4 years setting fire to things, which was quite fun. But I'm going to go back to basics here, and this is probably for most of your GCSE level chemistry, but it's quite a fun little area. So I'm going to draw the fire triangle, because you need three things in order to make fire. One side you need fuel, one side you need oxygen, another one you need heat. And let's use a match as an example. Get a fresh one out. The match head, or the match itself, made of wood, it's flammable. The head is a special mixture which is designed to set on fire when you give it a source of heat, which is the friction when you strike it against the sandpaper on the side of the matchbox. And the oxygen naturally comes from the air. When you mix those three things together, so you might get the thing to strike. Stupid thing. There we go. We end up with fire, and once the fire is burning, the match will burn the wood at a much slower rate than the initial fizzle you get with the match head. You should get a nice little smoke screen effect there. But all these things combine to give us a chain reaction. That's what fire is. A fire is a chain reaction. Now, chemically, fire is a ridiculously complicated thing, which I won't go into in this video. I'm just going to try and keep things simple. So what I'm going to do is take the simplest hydrocarbon, which is methane, CH4, which looks like tetrahedral molecule, so central carbon with 4 hydrogens around it. And let's burn this in an excess of oxygen, like, say, when you turn your gas hob on. Natural gas is mostly methane. The smell that you get from that is due to a small amount of a sulfur compound in, so you can actually detect the smell of gas, because otherwise you wouldn't be able to detect it and the houses would blow up more often, but that's a bad thing. So let's assume that we're going to burn methane in oxygen. So what do we get from this? Let's write that bigger down there and add a few O2s to it. Now, the products of complete combustion, like as in everything is burning fully, are carbon dioxide and water. Now, you can always figure out what ratio between these you're going to get from how many carbons and hydrogens are in the starting material. So we've got 1 carbon, so we're only going to make 1 CO2, but we've got 4 hydrogens, so we're going to need to make 2 waters. Now, what this means is we need to figure out how much O2 we're going to need. So if you ever need to work this out, it's you need 1 O2 for every carbon atom, and then 1 O2 for every 4 hydrogens. So with methane, we basically just need 2, like so. Now, if you're in a situation where you don't have enough oxygen, say in the middle of a house fire, or some other situation where your fuel is quite rich, everything's quite hot, so we've effectively removed the oxygen. Everything can remain there, and so you open a door and let a load more oxygen in, it's going to let the fire get big again, and you can end up with flashbacks and things go bang, and it's not pretty. So, under situations where we don't have quite as much oxygen, what we're going to get next is CO and the same water. Now, we'll call this partial combustion, because we're burning most of the methane into gaseous products, but not all of it. And this is part of the problem. Carbon monoxide is not a nice gas. It's what kills people when gas fires go wrong. So in this situation, we've lost one of the oxygens. Say we've only got enough for 1.5 oxygens for each each methane molecule, then we're going to produce carbon monoxide, which is bad. You'll get a mix of products from this. Don't take it as verbatim that you're going to get all of these reactions happening just one or the other or the other. In complete combustion, you will always get the top one, but if there's not enough oxygen, you'll get a mix of all the products. And if there's even less oxygen present, so say we've only got one oxygen for each methane present, what can happen then is we just produce carbon, which it's not single atoms of carbon floating around. It's they tend to stick together and form what are called polycyclic aromatic hydrocarbons, or PAR, PAHs, PARs. And these, this is an incomplete combustion reaction, by the way. These things stick in your lungs and can cause cancer and all manner of things, so they're really, not very nice. Those two are just bad. That's good from a combustion point of view, although not good for global warming purposes, which is why we're trying to move away from fossil fuels. But hopefully that will give an idea of the basics of fire. I've given the first practical demonstration, actually, with a pack of kitchen matches. And the simple thing is, with fire, if you remove any one of the three things which are causing it, oxygen, fuel, or heat, you can basically kill the fire. So if you get rid of the oxygen, you've got hot fuel, but it's not going to burn in the presence of oxygen. You get rid of the heat, that's generally how fire extinguishers work. You take away the heat, the fire stops burning. Or you take away the fuel, same thing. There are some complicated ways of killing the fire reaction, but I won't go into that here. I can do a video on how a bit more detail on the actual reaction mechanisms involved in fire if people are interested in that. But until then, I hope you've enjoyed this. I will try and post more regular videos as and when I can. But yeah, thanks for watching. Please like the video, subscribe, and share it to promote my channel. Thank you very much, and good night.